Hello class. In this video I'm going to work on the problems that are in your guided notes, and while you watch the video you should have the guided notes printed out in front of you or on a tablet, and writing your own notes, filling it in on your own, either with pencil or with a tablet, and then save those completed guided notes to be submitted later in the semester. And then once you've finished going through the guided notes and going through this video, you can do the week 2 homework assignment. Okay, so question number 1. This week, by the way, focuses still on problem solving, but with an emphasis on pattern recognition and using that recognition to make predictions. Task 1 here is to identify the pattern and predict the indicated terms. So we're given 4 numbers in a row, imply that this list would continue, and we were asked to find the 5th term, so that's in essentially the next term in this list, and then skip ahead to the 10th term, and then see if we can't come up with a way to jump ahead to the 1000th term. And we will do our best to do this without using any technology, and also with a mindset of being efficient with our time. All right, so the first thing you want to do is just look at this list of numbers and try to identify a pattern. It would be a good idea for you to pause the video right now and work this out on your own, and then come back to the video and see how I think about it. The first things I look for generally when trying to find a pattern is there some sort of pattern of addition that goes from term to term? If I can't find a pattern of addition, I think of a pattern of subtraction, or a pattern of multiplication, or a pattern of division, some sort of operation that's happening to go from term to term, so I can make predictions about what the future terms would look like. Well, in this particular case, to go from 3 to 10, if I'm thinking addition, I do see that I just need to add 7. And then that happens to continue here as well, and here as well. So this appears to be a pattern of addition, meaning that the next term, if I just add 7 again to 24, I should arrive at the 5th term. And 24 plus 7 gives us 31. Okay, so I'm going to write down, you can put a 31 here in your guided notes, or you can write this. Or to answer question A, you would say 31 is the 5th term, or put something in your notes that clearly establishes we just found the 5th term. I'll do this. We'll put a 31 here as well, keep our list going. All right, next it asks us to determine what the 10th term is. And so one way to do this would be to just continue the pattern until I get there. All right, so if we add 7 to 31, right, we get 38. Add 7 to 38, we get 45. Add 7 to 45, we get 52. Add 7 to 52, we get 59. And then we just have to make sure that we haven't skipped, or we've done enough terms to get to the 10th, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we do need one more. So erase those. Add 7 one more time, and we get 66. All right, so I would say the 10th term is 66. But part C is going to shake things up a bit here, because it asks for the 1000th term, and I don't think any of us want to spend our time making this list until I find the 1000th term. So we're going to have to rethink or think about this in a different way and try to be creative. Give yourself some time to ponder how you might approach this, and then come back to the video and let's discuss together one approach here. So looking here, define the first term's 3, but to find the next term we add 7, and then we keep adding 7. I do notice then to go from 3 straight to that 17, what would I need to do? I would have to add 2 7s, right, to go 2 steps down. To start at the 3 and go to the 24, I'd have to add 3 7s. Okay, so we start to, maybe this is a new way we could do this. Always starting at 3 and just trying to count how many 7s I need to add to get to whatever term I'm looking for. So I'm going to come down here and make a list. So this is the term number, and this is the actual, or how do we want to say this? This is the term. I'm going to make a table, a term number and the actual number. Hopefully this will make sense here when I start filling in this table. So for example, when I put a 1 here, this just means, hey, what's the first term? The first term is 3 in our list. Term number 2, what's the next number? Well, the next number, instead of just putting a 10 here, sometimes it's good to leave the operation in place. We got to 10 by taking 3 and adding 7, because we want to try to find a pattern in the operations. To get to the third term, we took this term right here, which is 3 plus 7, and we added another 7. Or you can think of it this way. We took this term and added 7 twice. Right? You can see how that's the same thing as starting here and adding 1 7, or starting here and adding 2 7s. But we can do some multiplication here, because adding 7 and 7 is like adding 2 7s. So we could just say this is 3 plus adding 2 times 7, adding 2 7s to 3. To find the fourth term, right, I can take the third term, which was this, and add another 7. Let me just copy that. So that's like saying we're going to take 3 and add to it 3 7s. That's like starting right here and just adding 3 7s to it to skip 3 positions in our list, to go forward 3 positions. Okay, I'm going to start simplifying a little bit. To get to the fifth term, we start with 3 and we add 1, 2, 3. We add 4 7s, right, to get to this number. To get to the sixth, we started with 3 and predict how many 7s do we add to get to the 6th position. 5 7s. And we start being able to come up with a pattern. What if I skipped ahead and said, hey, what's the 10th term in this list? According to this pattern, it would be take 3 and add it to, well, how many 7s get added to 3 to go from the 1st to the 10th position, and it's going to be 9 7s. In case you didn't pick up on that pattern yet, notice the following. I want to highlight the connection between this, how many 7s we add, and what number term we're on. Right? The number of 7s that we're adding to 3 compared to the number term we're on. The number of 7s we're adding to 3 compared to the number term that we're on. You can see that the number of 7s that we need to add to 3 is always one number less than the number term that we're looking for. That's what allowed me to determine that, to make a prediction that if I added 9 7s to 3, that would take me to the 10th term in our list. This is something that we can actually turn into a formula. Oh, by the way, before I do that, let's go ahead and, let me extend my table a little bit. Let's go ahead and actually do this calculation this way and confirm that we get the same result that we got here by simply just going out this list until we had 10 numbers. So So 9 times 7 is 63, and then add 3 to that is 66. Right, so this does confirm, right, that the 10th term of our list is going to be 66. The 5th term was 31, so let's look at this calculation right here and just build our confidence here. 4 times 7 is 28, add 3, 31, right? Confirming what we got just by adding 7 to the 4th term. We could generalize this and make a formula. If I'm on the nth term, then I would need to add n minus 1 sevens to 3. And if you remember distributive properties of algebra, you could rewrite this as 3 plus, we would have to do 7 times n, which is 7n, and then minus 7. And this winds up being 7n, and then we can combine the 3 and the negative 7 to make negative 4. This gives us a formula that we can use to find any term we want. Let's test it on some of these early ones. Begin by plugging in n equals 1 into this formula. Plug in n equals 1. N is essentially identifying which term we're looking for. So if we're looking for the first term, plug in n equals 1. 7 times 1 and minus 4. It does confirm that 3 is the first term. Plug in n equals 2 here. 2 times 7 is 14, minus 4 is 10. Right? It confirms that we get 10 as the second term, etc. Plug in 3. 7 times 3. Right, let's go here and plug 3 in for the n instead. 7 times 3 is 21. Minus 4 is 17. Is that what we get by this calculation? 2 times 7 is 14 plus 3. Yeah, we get 17 as well. Right, confirming that 17 was in fact the third number in this list. Okay, so we've come up with a general formula we can use, and we can certainly use this now to figure out what the 1,000th term. To get to the 1,000th term, I would add 999 sevens to 3. This is one way to do this. That's using this idea. Or we could also do just plug in 1,000 for this end, which actually I think is easier to do, because doing 7 times 999 without a calculator is not very pleasant, but doing 7 times 1,000 is certainly nice. So we get 7,000, and then we just have to minus 4, so we get 6,996. And this should be the 1,000th term in our list. All right, let's move to the next one. This is a similar instructions. Identify the pattern and predict the indicated terms. So if I'm looking at a pattern of addition, I see that we add 4 to go from 2 to 6. And then we add 12 to go from 6 to 18. Ooh, and then we add, what do we add to 18 to get 54? Well, if I add 30, it gives me to 48, and I need 6 more, so add 36. Is there a clear pattern in what we're adding to go from term to term? This is a valid question that maybe has an answer. But to go from 4 to 12 to 36, I'm thinking, how do we do that? If you don't see an obvious pattern of addition, think of, subtraction. Well, subtraction doesn't apply here because the numbers are getting bigger. So then think multiplication. Right, to go from 2 to 6, we can multiply, I'll put dot for multiplication, multiply by 3. Ooh, notice this. We multiply 6 by 3, we get 18. Is it true also that if we multiply 18 by 3, we get 54? We can double check that. 3 times 18, that's like doing 3 times 10 and adding to that 3 times 8. So we get 30 there, and we get 24 here, and that adds to 54. Yeah, so 3 times 18 is 54. So this appears to be a clear pattern of multiplication. So multiply by 3 again to get to the next term, which is the 5th term. Okay, so doing 3 times 54. By the way, I'm using a shortcut. When I say 3 times 54, I'm breaking 54 up into 2 parts that are easy to keep track of, 50 and 4. And then I'm effectively using the distributive property. So I just got to do 3 50s and also do 3 4s. So this becomes a quick way to do some arithmetic. 3 50s is 150 and 3 4s is 12, and put those together and we get 162. Right, so that would be the next number in this list, 162. And when you're doing your guided notes, you can be a little bit neater than what I do here. This video is just to talk about ideas, but I want you to present your answers in neater presentations than what you're seeing me do here, just for the record. Then we've got a triple 162. So we can triple 100, triple 60, and triple 2 and add all those together. Triple 100 is 300, triple 60 is 180, so that takes us to 480, and triple 2 is 6, so 486. And this is going to get more and more tedious, obviously, as we continue. So feel free to use a calculator to try to get to the 10th number of this list. But I'm actually going to save that. I'm going to answer question C next, and then use a formula to get to the 10th number in this list. To do this, I'm going to repeat something similar to what we did before. So we're going to have the term number, make a table that is, and then the actual number in the list. Okay, so the first term of this list was 2. The second term in this list was 2 times 3. Remember, don't just write 6. Write down the operation uncalculated, because we're looking for a pattern in the operation. The third term in this list was found by taking the one before it, which is 2 times 3, and multiplying by another 3. In other words, starting with 2 and multiplying by 3 twice. Right, to get to this 18, we tripled and then tripled. Right, so the fourth term is 2 times 3 times 3 times a third 3. And a pattern is quickly emerging here. If we were to use exponents to summarize some of these, right, this would be 2 times 3 squared. The next one would be 2 times 3 cubed. The fifth term would be 2 times 3 to the fourth. Right, because we'd have to multiply 2 by 4 3s, by 3 times 3 times 3 times 3, right, to get to the fifth term. And we're quickly able to come up with a pattern for the nth. Again, notice the exponent that's on 3 compared to the term that we're looking for. The exponent on 3 compared to the term we're looking for. The exponent on 3 is always one number less than the term we're looking for. So if I'm looking for the nth term, I would do 2 times 3 raised to the n minus 1 to keep up with that pattern. Right, and this is going to allow me now to jump to the 10th term. According to this formula here, we would do 2, and then we'd multiply 2 by 3, and if I were to write them all out, right, there'd be 9 3s here, because we need to do 9 steps to go from the first term to the 10th term. Of course, I don't want to write all those 3s, so that's why we're using exponents instead. There'd be 9 3s we need to multiply. Now I'm going to go ahead and actually just reach for a calculator to make this a little bit easier. My calculator of choice is this Desmos. It's a free graphing calculator that also does calculations. And we wanted to do 2 times 3 raised to the 9th power. So this would wind up being that 10th number in the list, 39,366. 39,366. Always double check I wrote things down correct. Okay. And that way I actually answered question C first, and then I used my result there to get question 10. The temptation, though, was to answer question B first, and I could have done that easily, right, by just continuing this pattern until I got to the 10th term. And I encourage you to do that as well with your calculator and confirm that our formulaic approach produced the same result. All right, let's go on to the next slide, the next page here. Identify the pattern and predict the indicated terms. I'm going to pause. I encourage you to pause the video and to try to work this one out completely on your own, and then when you feel like you've given it enough time, come back and see what I did here. All right, looking for patterns. If I'm thinking addition, right, here we added 0, then we added 1, and then we added 1 again, and then we added 2, and then we added 3, and then we added 5. Oh, this is interesting. I don't know if you've noticed what I noticed. But the numbers that we're adding, not counting the 0, right, just looking at those, is a repeat of these numbers, which allows me to make a prediction that to get to the next one, I should add, well, whatever was next in this list. So after the 5 was an 8. So if we add 8, that would take us to 21. And then I want to add 13, because that's the next number in this list. And 21 plus 13 is 34. So it appears that we've identified a pattern that's going to allow us to predict more and more terms. Another way to look at this particular list of numbers is not counting the first two, right? Don't ignore those. Those are just 1 and 1. But starting with the third one, you can find that number by adding the two numbers that were before it, right? So add 1 and 1, and it makes that 2. Now to get the next one, add 1 and 2, and it gets that 3. And then we add 2 and 3, right, and we get that 5. So here's another way you could look at this. You know, add 8 and 13, and we get the 21. Now we add 13 and 21, and we get the 34. Let's continue this way of thinking. Add 21 and 34, and that takes us to 55. Now add 34 and 55, and we get to 89. And let's make sure that we know what we're trying to accomplish here. Find the 8th term. Well, the 8th term was the next term, so right there is the 8th term. Count them out. 1, 2, 3, 4, 5, 6, 7, 8, yes. And we're looking for the 12th term, so that's 9, 10, 11. So we just need one more to get to the 12th. And we get that by adding these two numbers. And 189 plus 55. We'll take 1 away from the 55 and combine that to the 89. That makes 90. And then add 54 to 90, and we get 144. Oops. And this is our 12th term. They're having some issues. All right. And this one doesn't ask us to predict what the nth term was. This one would actually be quite complicated to do so at this point, and so I didn't bother asking it. It's not always possible that we can come up with a formula to predict a term, you know, later in the sequence, like what the nth term. If I'd asked you for the 100th term of the sequence, the only way I personally know how to do it in this case, well, the only way that's feasible for us in this class is to actually add up just keep the pattern going until we have found the 100th term. Then it turns out there are mathematical ways to come up with a formula that would go straight to the 100th term, but those are beyond the scope of this class. By the way, this particular list of numbers is called the Fibonacci numbers. You might have heard of them before. The Fibonacci numbers are the numbers, they were made I guess, popular and mainstream by the movie The Da Vinci Code. But anyway, there they are. Moving on, number 4 here in our list, use at least 2 methods for determining a formula for predicting the result. Okay, so now we're adding 1 plus 2 plus 3 plus 4, and we're ending at n. So what does that even mean? These are known, by the way, I'm about to make a list of numbers known as the triangular numbers. Let's say we have a single 1 all by itself. There'd be 1 dot. Now we're going to make a triangle of numbers. Notice how this represents 1 plus 2. And there are 3 dots. Now if I want to represent what 1 plus 2 plus 3 is, there's 3 dots, 2 dots, 1 dot, and you add those together and we get 6. If I keep this up and make a triangle that has 4 levels, right, this represents 1 plus 2 plus 3 plus 4, and that gives me 10. Notice this pattern. To go from 1 to 3, we add 2. To go to 3 to 6, we add 3. To go from 6 to 10, we add 4. You see a pattern here? What do you suspect we're going to add to go from 10 to the next number? Probably add 5, which makes perfect sense because the very next triangle I would draw would be this same triangle, but with an extra row on the bottom that would have 1 more than the last bottom row. So it'd have 5 dots. So what this task here is asking us to do now is to determine a formula for predicting the result if I get to the nth such triangle. So let me move these down. Right, this would be the first number in this list. This would be the second number in this list. This would be the third. This would be the fourth. This would be the 5th number. We're trying to skip ahead and predict what the nth. Right, it's kind of hard to make such a triangle because we don't know how many dots there would be here. But coming up with a formula for this, the sum of these entries, 1 plus 2 plus 3. Right, so do you see, make sure you can see in this imagery the 1 plus 2 plus 3, right? There's the 1, there's the 2, there's the 3, the next row is 4, etc. This last one would have n. And let me make these notes a little bit smaller, move them up over here, so I have some space to work. Now this says use at least 2 methods for determining a formula for predicting the result. I'm going to illustrate a visual way and then an algebraic way of doing this. Let's go with the algebraic way first. Okay, so let's say that this adds up to some unknown number that we're going to call capital A. So we have A is equal to 1 plus 2 plus 3 plus etc. up until we get to n. I could rewrite A a different way. I could write it backwards. I could start at n and then count down. Before I do this, though, let's quickly determine what a valid expression would be for the one before the last one. Like, what would you want to put right here in this position? Well, if n is the last number and we've just been going up by 1, then it stands to reason that n minus 1 would be the number right before n. Right, so there'd be I'll put it in parentheses, there'd be an n minus 1 as the second to last entry there. Oops. And n minus 1. So doing this sum backwards, if we start with n, then the next one down would be n minus 1, and then after that would be n minus 2, etc. The second to last number in this list would be 2, and the very last in this list would be 1. So I just flipped the numbers around. If you're having trouble seeing this with the n's, imagine doing this with 1 plus 2 plus 3 plus 4, which we know the answer is going to be this 10, the 10th number in this list. But look what would happen if I reversed it. And let's pretend that I don't know what this number is. I know the answer is going to be 10. And if I add them this way versus add them this way, it won't matter. I'll still get 10. But when I put them together like this, and then I add by column, a plus a gives me twice the number I'm looking for. But when I add 1 with 4, I get 5. When I add 2 and 3, I get 5. When I add 3 and 2, I get 5. When I add 4 and 1, I get 5. Well, this is fascinating that I get the exact same number for all of these. Which means I can use multiplication, right, to get this. 5 plus 5 plus 5 plus 5 is 20. And that's twice the number I'm looking for. So now I divide both sides by 2, and I get that the number I'm looking for is actually 10. Right, so if you can see this magic happen when you simply flip the order of the sum around and then add it to itself, we're going to get some interesting results here in just a moment. By the way, the technique I just used here was I simplified the scenario and made sense of it. And this is one of the strategies mentioned in the last lecture about problem solving. So now I think I'm in a better position to think more generally over here when there's an n involved. So I'm still going to add the two rows and by column by column. So a plus a gives me twice what I'm looking for. And then, all right, add n and 1, and we get, oops, let me switch to the pen. We get n plus 1. I'm going to put it in parentheses. Then add 2 and n minus 1. Well, if you take n minus 1 and you add 2 to that, it's going to take it back up to n plus 1. So we have another copy of n plus 1 by adding the second column. Third column, we have n minus 2 and 3. If we have n minus 2 and I add 3 to that, that's going to take it back up to n minus 1. And we should get n minus 1s all across the board. Look at the second to last, and then the last. Add those. N minus 1 plus 2 also takes us to n plus 1. And then the last one, just n plus 1. Right, the next question here is, okay, well, how many n plus 1s did I just wind up getting? Well, how many numbers are in this list? Well, it's really easy to count because they just count themselves out. 1, 2, 3. There's n numbers in that list. Right? If you add n, so that means there's n numbers in this list. There's n copies of n plus 1. So that allows me to use multiplication instead. So we have twice the number I'm looking for is equal to n times n plus 1. It's n copies of n plus 1. And then finally, I want a to be half that. So 1/2, or you can put it all over a 2, of n times n plus 1. Right? Or you could write this. I don't mean to have a plus there. Right? An equal sign. So these are saying the same thing. You do n times n plus 1 and then divide it by 2, or you do 1/2 of the product of n and n plus 1. So just be comfortable with that. I'm going to leave the first one only. I call this an algebraic approach for determining that when I add these numbers together, I do in fact get 1/2 of n times n plus 1. Let's test it for small values of n. Now let's try to confirm that we get 10 when I'm at the fourth number in this list. In other words, we're going to confirm that 1 plus 2 plus 3 plus 4 does give me 10 if I do the following formula. I do 1/2 of n being the last number, so 4, times the next number in the list, which would be 5. times n plus 1. Right? We're essentially finding the sum of 1 through n when n is 4. So in other words, 1 through 4. So we put a 4 there, which is the n, and then a 5 there, which is the n plus 1. And then we do that calculation. 1/2 of 4 times 5, so that's 1/2 of 4 is 2, and 2 times 5 is 10. It confirms the 10. Let's test the formula with the 5. So erase, there we go. So if I go until 5, now I know the answer is going to be this 15. But let's use the formula. It's 1/2 times the number that we're stopping at times, or I should say how many numbers are in this list, which is 5, times the next number that would be in that list, which is the n plus 1, which is 6 in this case. Let me put a 6 there. Right. And 5 times 6 is 30, and half of that is 15. Right? It confirms our 15. So I'm feeling fairly confident that we've come across the right formula for adding the first n numbers. If you'll recall, looking back at your homework from the last unit, you were asked to do this sum. But I asked you to problem solve this and come up with a couple ways of doing this. Well, using the formula we just generated, I could say, well, it's going to be 1/2 of 100 times 101. So this formula should produce the answer that you should have found doing that first homework. I'll let you look back at your homework and verify that. Oops. Let me get rid of all that. Delete. Okay, we were challenged to find, I didn't give myself a lot of space here, so when you're doing your guided notes, you can do this a little bit neater than I'm doing here and keep your work nice and distinct. I might actually move some of this stuff around to give myself a little more space. Let me just move that up here. Just kind of keep that out of the way. And let me show you, I'm going to actually show you two other ways of doing this. All right, so if we start at 1 and we go all the way to n, that means, again, the second to last term was n minus 1. But if we do this sort of alignment this way, I'm going to add first and last, and then add second and second to last, and then third and third to last, etc. Every time you do that, you just get another copy of n plus 1. But you're pairing off the numbers. So if you group them in pairs and add them together, you get n plus 1. And the question is, how many pairs do you have? Well, you had n numbers, and you paired them off, so divide that by 2. And this gives you a formula for seeing how many, what the total actual sum is. You just added them in a different way. Let me show this for a small number case. Let's stop here. Right, if I add 1 and 6, I get 7. When I add 2 and 5, I get 7 again. When I add 3 and 4, I get 7 again. So I'm just adding 7 a bunch of times. And the question is, well, how many 7s do I have? Well, I had 6 numbers in this list, but I paired them off, so I had 3 pairs. So if I do 3 times 7, I will get the right answer. So notice 7 is simply the next number that would have been in this list. So the next number that would have been in this list is n plus 1, so there's the n plus 1, and then you multiply by how many pairs there are, which is n halves. Now, the nice thing about this formula here is that it works even if you have an odd number. Like let's say we do it this way. Add 1 and 5, we get 6. Add 2 and 4, we get 6. And then we have 3. So I could only pair them off. I couldn't pair them off entirely because one number was odd man out. But we definitely see that I had 2 6s plus a 3. Well, the 3 is the same thing as a half of a 6. So it's like having 2 6s plus a half of 6. That's like saying you have 2 1/2 6s, which is the same thing as saying 5 halves 6s. So the formula still works. You do the last number of the list times the next number up and cut it in half. Or you can look at this and say, hey, I see 2 1/2 6s. Well, where did 2 1/2 come from? It came from cutting the number of terms in half. So you have 5 terms here, cut it in half, and then all the numbers add up to 6. So we have 2 1/2 6s. So it still works, the formula still works even when, or this way of thinking still applies even when you have an odd number of terms. Okay, and the last one I want to show you is a visualization of what's really happening here. Imagine you have a bunch of blocks, and I'm only going to draw up to 4. And let's say, though, that that represents n rows, and the bottom one is n units across, right? So there's 4 rows, and the bottom one has 4 across. Well, if I were to take this and copy it, and I'm going to spin it around as well, and let's also change the color, okay, and stack it right here. Make the size correct. No, that's good enough. You get the idea. When you take this stack and make a copy and flip it and put it together, you get a rectangle. And the question is how many squares are in this rectangle. And if you cut that number in half, you'll get how many red squares there are, which is what we're after. Right? But the brand new rectangle I've made, oops, that's not the marker I wanted. Let's go blue. There's actually n plus 1 columns now. So the total amount of squares in the red and green combined is n times n plus 1. But since I only want how many were in the red, if I cut that in half, that will tell me what 1 plus 2 plus 3, etc. is up until we get to n. Right, so I've actually shown you 3. In your guided notes, feel free to just do 2 of these, but here in our lecture, I've shown you now 3 different ways for determining that the sum of 1 through n is given by this formula that we have here. Okay. All right, find the sum below in 2 ways. Okay, let's go ahead and do this in 2 different ways. I'm going to put the numbers here, but I won't write all of them. This ends at 40, but the second to last one was 39, and then the last one was 40. Notice this trick of pairing. If I do 3 plus 40, or sorry, 13 plus 40, I get 53. If I do 14 plus 39, I also get 53. So the only thing I really have left to do here then is say, okay, well, how many am I always going to get 53? You know, if I do 15 plus 38, which I don't have written down, but if I did 15 and 38, I would get another 53. So the question is, right, how many 53s, right, total would I have if I wrote all the numbers down? Well, here we have to figure out how many numbers I have in this list. And then pair them off, so cut that in half. Well, if my list started at 1 and included the 12, etc., then there'd be an obvious 40 numbers in this list. And if I remove those, then I've removed 12 numbers. So if I had 40 numbers to begin with, and I just removed 12 of them, that means we should have 40 minus 12 numbers in this list, and that is a total of 28 numbers. All right, well, that helps me know that there's going to be 28 divided by 2, which is 14, pairs of 53, right? When I add these first and last, second and last, etc., I'm going to get 53 each time, and there's 14 pairs. So it should be true that this sum here is equal to 14 pairs of, and each pair added to 53. So 14 times 53. Let's go ahead and go to my calculator and do this calculation. 14 times 53. 14 times 53, we get 742. All right, so that's one way to do this. Another way is to, again, I'm going to put that 1 through 12 on here. And then 13 and on. Okay. I can use this information, or this formula that we have here, in a creative way. If I add 1 through n, I can use this formula to get the result. So if I start, and the sum has to start at 1, right, and end on n for this formula here to work. So if I put the first 12 back in this list, and I start at 1 and end at 40, then I know that this sum, total sum, is going to be 1/2 of the last number, which is 40, and then times the next number up. And we can get that by, again, or also doing the 1 plus 40 is 41, 2 plus 39 is 41. So you have all these 41s that you're adding together. And there's 40 numbers in this list, therefore there's 20 pairs. So here's the 20 pairs times the 41. But then if I apply that same formula, but just to the first 12, I would have, okay, well, we have 1/2 of 12, so there's 6 pairs, and each pair adds 13. Right, so I do 1 plus 12, 2 plus 11, right, 3 plus 10, etc. So I'm using the formula that we came up with twice. Therefore, the rest of this should be, let's make this a different color, green. The expression we have for all of it minus the stuff we just cut off, the expression we have for the first 12. Right, so here's another approach we can take. So this really is going to be 20 times 41, that's 820, minus, and we have 6 times 13, that's 78. If I do 820 minus 78, we'll take away 20 away, take 20 first, so it takes it down to 800, and then remove 58 from that, and we also get this 742 figure. Right, so here's just a second way to work through this task. Okay, let's do our very last problem here for this week, for our guided notes. Based on the evidence below, describe the meaning of the operator, which is the symbol a star, or an asterisk, and use this meaning to find the result of the last operation, then generalize the meaning using variables. Okay, again, this is a good time for you to pause the video and try this on your own, and then when you feel like you have something to work with, unpause the video and see what I do. All right, so something is happening to 1 and 4 to make a 7. And then we want to assume that same pattern happens to 2 and 5, it would make an 8, etc. So let's just start thinking things. How can I use a 1 and a 4 and get a 7? Well, what if I add them together? I don't get 7, I get 5. But if I add 2 more to that, I do get 7. So let me try this. If I add 2 and 5 and then add 2 more to, right, so repeat the pattern. And that's going to give me 9. Ooh, I don't like this already. If I add 6 and 10 and add 2 more to that, I get 18, right? So I'm not getting these results. So that was just a shot in the dark. If I try to involve multiplication, right? What if I multiply the two numbers and then add what's needed to get to that number. Let's see what happens here. So let's go 1 times 4. That's 4. Then I need to add 3 to that. That would give me 7. Let's keep up this pattern. If I do 2 times 5 and then add 3 to that, do I get, what do I get? 10 plus 3, I get 13. This doesn't seem to be working. Or maybe, instead of adding the same number, we need to add the number that's here that we added to 1 times 4. Maybe that needs to be one number less than that, the second number in our product. All right, so that would suggest I add 4 here, but 2 times 5 plus 4, no, that doesn't give me 8 either. All right, maybe I've given you some hints, things to think about. Pause the video, try to work this out. Pause the video anytime you feel like you want to try to finish this out on your own. What if I multiply the first number by 2, and then I add to it the second number? Oh, that only gives me 6, though, so that's no good. What if I multiply the first number by 3, and then add it to the second number? That does give me 7. Let's see if this works. On the next case. That gives me 11, does not give me 8. So I'm not liking this one either. I'll let you figure this out, but in the end, it's going to wind up being the following. 1 asterisk 4 means double the second number and remove the first. So if I double the 4 and remove the first, that gives me 7. Let's try 2 asterisk 5. Right, double the second number and then remove the first. And that gives me 8. Let's do 6 asterisk 10. Double the second number, which is 20, and remove the first. Ooh, okay, so this is working. And 9 asterisk 11 would be double the second number and remove the first. Well, 2 times 11 is 22. 22 minus 9 is 13. Okay, so I feel like we have a pattern that is consistent for the data that's presented, which is just these 4, and I'm going to now use it to do 1 asterisk 10. Let's double the second number and remove the first, and that gives me 19. Then x asterisk y would be double the second one and then remove the first. So here are the two answers that we were after here. All right, so this ends our lesson on pattern recognition and adding numbers like 1 through n and finding shortcuts for getting the result. And now it's up to you to complete your homework assignment.